Hello and welcome to Lecture 5, Part 2. So we've been talking about collections, that is groups of things. And last time we talked about, in Part 1, talked about groups of things in Scala, collections of Scala. We talked about things like seek and how we can use that in the hardware generation process, and how we can use also things like for loops as well to kind of navigate that space. Today we're going to shift gears and talk about collections in Chisel. How do we have those? And so let's go ahead and fire this up. So we'll get the notebook going. And then, yeah, let's um, jump into it, right? So one of the things that's always kind of good to keep an eye on in this course is when we have these various constructs, what is something that's in the Scala program while we're running the generator as opposed to what's something that's going to appear in the generated hardware? Because oftentimes this code's intermixed and it's kind of hard to keep track of which is which, so you have to have a clear picture of both. And so a chisel vec, which of course is short for vector, is something that's going to appear in the hardware. That's in contrast to the Scala seek we talked about earlier, which is something that's in the generator program, but it's not going to appear in the hardware, right? So what is a vec? A vec is, as the name implies, it's a vector, so you can have n elements into it. They're all going to have the same type. The key feature of it is, in addition to just having n elements, you can dynamically select an element, right? An index, right? In other words, in this generated hardware, you have the ability to address something within it, right? And so this concept, I think, is very clear to most people. I think where students get tripped up in past offerings is they think, oh, I want n things, let's use a vec. And the answer is you only need a vec if you need that addressing ability in the hardware. If you just need n things for generating, use the Scala seek. The vec is when you want that addressing ability, right? Um, so to see an example of it, why don't we actually just use a vec as a way to implement a mux, right? So we can build a n-way mux, n is the number of ways that's coming in. Each of those different inputs will actually be an input to the vec. So that way we have, our n-way input here, and we can select from it, right? And of course, the selection operation for vec is using the indexing notation. Even independent of chisel, in Scala, you index into arrays using the round parentheses rather than square brackets like a lot of other languages. So yeah, we can go ahead and make, an n-way mux easy, right? In this case, we have a 4-to-1. Degenerated chisel is going to have a bunch of 2-to-1s. That might seem less efficient. Don't worry. The hardware CAD tools, they see this, they're going to go ahead and optimize that, eat that up. They'll do the right thing. But this is a parameterized, right? We can go ahead and make this, 8 inputs, no problem. I can also change the bit width. Right now it's 1 bit wide. I can make these all 4 bits wide. So here's already an example of, some parameterization is really helpful. Some other things to point out about vec. So vec is a type, not a physical thing. Even though I mentioned this ability to dynamically index. So the reason why this nuance comes up is, let's say you want to have n registers and index them in hardware, while the hardware is existing. You might think, oh, I want a vector of registers. And conceptually, I think that is a reasonable assumption. However, in terms of the way the types interact, it's actually technically a reg, and the type of the register is a vec, right? So it's a little bit, it's the inverse of what you expect. So if you try to do vec of reg, the tools will tell you can't do that. You need to do reg of vec. This is an extremely common point of confusion. Um, Same is also true if you want to do a wire. If you want to have a bunch of things in the vec and a wire, you put the wire on the outside. And so for now, you can just try to remember and make a note of that. If you forget, the tools will tell you and you invert it. Um, for those of you who are really excited about programming languages and stuff, if you want to dig into this, there's reasons why, and with the type elaboration and stuff, that this is the order it needs to be done in. Um, cool. Questions on Vex so far? Great. Let's just kind of see some more examples of it. Let's say, for example, I want to build a hardware to do reductions, right? So reduction is the ability to take, n things and reduce it down to one thing. Most commonly, that reduction operation is an addition, but that's technically not a requirement for reduction. So let's say I want to have an n-way reduction, sum reduction, right? Okay, great. So I'm going to have n inputs, and then I'm also have n minus one adders to add them all up. So how can I go about doing this? Well, with a vec, we can have this parameterized number of inputs to kind of match that. Sure, great. Like I said, you can think about this. Wait a second. It's a vec with n elements and each element is a uint of width w. That's like is going to be, n times w bits, right? It's a lot of bits. And then the output, of course, is a single element, sure. And so how do we do all this? Well, we need to make sure we have at least one port. That's the requirement statement. And then I chose to, in this case, to do a var with a for loop, right? That's not the only way to do this, but that's a nice way to do this, right? And so we can take the first input and then from then onwards, just keep adding things on. So we're gonna get this unbalanced tree. Yeah, so how does this actually look in hardware? Well, hey, gee, if I only have two things, it looks like how we hope it would look, right? Just a simple addition. Now, if I was to, add things on, okay, we start seeing additional additions. And yeah, it grows as you would expect. And of course, yes, the bit is also parameterized. Right now, we're all used to that. It's trivial. Um, cool. Questions so far? Cool. Yes. Good question. So when I use a vec, the name of this output variable seems to be a little bit, undefined or defined by the Chisel compiler. Yes, it's definitely defined by the Chisel compiler. The Chisel compiler tries to follow certain programmatic ways of naming things. Um, it also is on the hook to make correct Verilog. So sometimes what you think the correct name should be may already be in use, for example. And as a collision, it detects that and has a way to kind of get around that. And so in this case, yes, you can see that it chose to take the io.in and put an underscore for the dot. That's a pretty typical transformation. And then because there was a vec, it did another underscore and then the index, right? So that's the way it happened to make this name. Some other names are not quite so obvious. You can kind of see, for example, like total so far, which is a Scala reference, and you keep changing what it points to. That appears as underscore T1, underscore T3. So a leading underscore is something where this is a name the Chisel compiler generated. It's not something from your code. Your code created that, but didn't actually have that name. If you are really concerned about the names of things in the Verilog, there are ways to annotate your Scala code to suggest names of certain key crucial things. So it's too much work to do for everything, but if a certain port to one of a certain name, yeah, you can do that. Okay, yeah. So number one, two questions, right? Number one, the question of choice of var. Number two, what about a register? So let's attack the var thing first. Yeah. So the var thing, even though I keep hyping up using val, here I'm using var. Um, we'll see this hardware again in a few lectures when I teach more constructs, and so we'll go farther down the functional programming path, and I'll show you how to do things like a fold, and that way we don't need to use a var. We also can use recursion to avoid using a var. So the var can be avoided, but for what we've covered so far, and this code is perfectly reasonable code. I think this is a perfectly fine use of it. In terms of a register, there's no reason why we couldn't use a register, but that would change the semantics, right? So right now, these are all adders. Those are combinational components, right? So they produce their output. There's some physical delay, but it's not dependent on the clock period, right? It's going to be whatever time that takes. So 1 hour delay, 2 hour delays, n minus 1 hour delays. If I put a register in there, all of a sudden the data advancement stops at the register until the next clock cycle, right? It's that clock barrier. Um, Depending on your implementation, that may or may not be a good thing, right? And so, yeah, depending on what you want, yeah, go ahead and do that. You may be in a situation, let's say you have 64, inputs to reduction unit, and maybe they're all 64 bits, 64 adders in sequence, or 63 adders, I should say. That's going to be a very long critical path. So for timing reasons in hardware, you may put in a register to break up and pipeline it. Once again, up to you. But for right now, like I said, the chisel is going to be whatever you tell it is, right? So if I describe this as combinational logic as the registers, it's not going to put any registers in there. If I put registers in there, it's going to keep them in there. And so, yeah, it's up to you as a designer what you want. Cool. Okay, then, um, so that was a vec. Now, one scenario you may want a vec is let's say you want to have a read-only memory, a ROM, so to speak. There's a vec init helper function lets you help you do that, right? So in other words, you can give it a sequence, and what it's going to do is it's going to create a vec of that sequence. So that way in hardware, you can address that data. So vec init is going to initialize wires. In other words, these are all going to be constants. If you want to have registers and initialize all those registers in parallel, there's actually also a reg in it. But anyways, let's go back in example first, right? So let's say I want to build a table in hardware that does division, right? So in other words, rather than building a hardware divider and build a ROM that does that divider for us, that might be cheaper than actually building a real divider. And so it's not going to do the full division. It's just going to remember, is this thing divisible by something, right? So given some input in, it's going to say, is that divisible by X, the thing we did a generator for? Okay, so you can see we're going to build up this sequence. This is the use of var I do not like, but I'm doing it because I haven't covered enough Scala to avoid it yet. So here I'm once again using a var because I have to, but we will see in not too long, even later today, how to avoid using this var. But okay, what am I doing? I'm going to build up this sequence that is going to contain uh, bools of whether something divides evenly. So what am I seeing who divides who? I'm taking, what is the remainder of, I and X. So I is this loop iteration variable. Let's say we're deciding to make this table 15 elements big. This probably should be a parameter, but for now we're just doing a hard-coded literal. So 16, the first 16 numbers, and we're seeing, is the remainder zero, or is it divided evenly? And if so, it's a true, otherwise it's false, and return that into a chisel bool. This syntax is a small detail, it's not super critical, but this is how they, in Scala, chose to represent appending an element to a collection. And that symbol may look kind of funny at first, like, wait, colon plus? I haven't seen that. Someone was very clever. So basically, you put the colon on the side that has a collection. So if you have a collection and you're adding on an element, it's colon plus, right? Because the colon is on the side of the collection and the plus is on the side of a single element. You actually can also prepend an element and then it's, plus colon, right? That's also the case. And then if you have two collections, like you're doing on cons in a lot of languages, that's colon colon. So there's two collections on both sides. So that's, Scala being very ornate. But we won't use this pattern too often in our code to build up sequences. You'll see later today how to build up a sequence without using a var. Without using a var, you don't need to worry about this construct. You can use the recursion too, but we won't need to use it too often. But for now, just trust, okay, we built this sequence. It has 16 elements. We turned it into this vec init, and now we have a ROM. So we'll go ahead and run this and look at the table. Yeah, it creates this ROM for us, right? And so uh, you can see that under the hood, Chisel compiler turned this into a bunch of muxes, right? Hey, is the input one? If so, um, return something, right? Is it two? And you can see it's kind of this unbalanced tree of muxes. It's also doing a selection procedure here. Like I said, I'm sure people are kind of worried, oh my gosh, is that going to be inefficient hardware? Trust me, the hardware cat tools will see a bunch of 2-to-1 muxes and do the right agglomeration. This makes sense for technology you're using. What's actually more surprising to me is, so for research in our group, we have been building a tool that takes in the Fertile from Chisel and generates Swift Plus code to make a high performance simulator. And so, yeah, so we have these large vex and user designs, maybe 1,000 elements, that turns into 1,000 of these 2-to-1 muxes in the Fertile. One that gets generated Swift Plus that turns into 1,000 if statements in our code. And then compilers like Clang are smart enough to see 1,000 deep if statement and turn it into an array access. That's like a C compiler. So the hardware tools, this is even more important for them. They can do it. But the key point is, yeah, it works. You can see that along the way, it keeps referencing prior results as it kind of works its way in. But yeah, we can change what these parameters are, and it kind of comes together. But this is an example of just building a ROM. Usually, you aren't looking at this very long. As you can see, it's machine generated, not very helpful to humans, but the chisel kind of hopefully makes sense. Questions? Okay, let's see what else we can do. So we just talked about a vec, which gives you the ability to have a one-dimensional element thing you can index into. Now a mem, short for memory, does two things. Not only does it have dynamic addressing, that's in you can index things in hardware while it's existing, but it's also actually stateful, right? It has memory. And so depending on which memory you want, you actually can get different types of memories, right? So remember in hardware, when we build state elements, we have registers and SRAMs, right? Static, read only or read access, random access memory. Sorry. And so with registers, remember the combination. The result is that you can read register instantly, right? It's always output coming out of it. So it's a 0 cycle delay to read the data. However, the data is put into register over some amount of time, right? It takes a cycle to get in there. Versus a SRAM takes both a cycle to get in and also takes a cycle to read it as well. And so if in Chisel you say, hey, I want a mem, by default, it's going to give you a combinational read memory, i.e. 0 cycle delay. So it's actually going to be basically registers that have methods attached to them, essentially, right? Alternatively, if you want to have that 1 cycle delay and have it be mapped to SRAM, you can use a construct for a sync read mem. You can also use a mem and you can change the delay with a parameter, and you can make it an arbitrary number of cycles. You can make it 2 or 4 cycle delay, which maybe better matches the technology you have in your design. And we'll see some examples, but MEMS are pretty nice. So in Chisel, you can have this very fluid way of working with them where you can just kind of access it however you need to, both for reads or writes, and the ports are declared implicitly as you're using them. Some people don't like that design style, and they instead prefer to have very explicit memory ports. Also okay. And yeah, I can do things like write mass and all that other good stuff. Let's go ahead and see some examples. So let's say I want to build a registry file for a processor, right? So for your canonical RISC style processor, you're going to want to have 2 reads and 1 write at a time, right? And let's say you have 32 registers, right? Well, how would you do this? Well, for that registry file, you have already quite a bit of ports, right? You need to have the register numbers for the 2 inputs, right? Register 0, register 1. These are 5 bits because it's going to be 32 registers. You also need to have the 5-bit index for which register you're going to write to. And you don't always want to write, so you want to have an input to say, is the write enable on or not for the write port? And also, if you are going to do that write, you need to give it the data, 64 bits of the data you're actually going to do. On the other end, of course, also after your reads, you're going to have your outputs, right? So you have, the outputs for register 0 and register 1. So here's us explaining this with reg of vec, a perfectly reasonable way to do this. You see it comes together. It's actually pretty concise syntax, right? We declare the registers. And then for the read ports, you simply just attach these outputs to the registers and whatever index is coming in. In this case, there's not any kind of read enabled because the way it's implemented, there's no damage caused by doing a read if you don't intend to do a read. If you don't want to read, don't look at the output. It doesn't matter. And then, of course, for the writes, you only want to do writes when we want to, in which case then we can use the write enable. And then if the write enable is true, then yes, we modify the contents of that location with the incoming data. So this is a pretty concise little bit of code to do registry file. And yeah, look at the Verilog. You can imagine what it looks like, right? It declares 64 registers. There's all of these muxes to select who's talking to who. Yikes. Um, Alternatively, so this hardware-wise is going to be plenty efficient, but the Verilog, as humans reading it, we hate it. Uh, if I use this mem construct, uh, it's going to be a little bit more tidy. Notice how it's already using the Verilog construct of having an array. So there's 32 of these elements of reg 64 bits. And so the result, yeah, the code's a lot more concise. You can see that, the read ports, for example, are like this. There are still quite a few wires here. That's because the tools are, declaring all the various wires required to support a port to memory. In terms of the generated hardware, these two things should be nearly equivalent. They're both going to be registers because SRAMs typically have a synchronous read delay, but just kind of showing features, right? So if I want to have 32 stateful elements, regevec is totally fair game. A lot of times you think of regevec, if you forget, regevec, vec of reg, just do a mem and you're done. Cool. Questions? Okay, so let's keep going. So that was with implicit ports. You can see how, for example, we just access what we want to access. What if we want to make it more explicit? So yeah, you'll like this more verbose syntax where I can say, I'm definitely doing a read and I'm definitely doing it right. Um, it just makes it more clear what the operation is. Draw attention to the fact this isn't just some sort of index. Is actually like a read or a write to a memory. And yeah, the code coming out the other end is exactly the same. Um, cool. Yes. Oh yeah. So good question. So I chose to have like the naming like such where I have R0. That's just a style choice I did in this particular case where yeah, register zero, register one, address. You could also imagine it being register address zero, register address one. To me, conceptually, I think R0 is more closely binded than the R and the address, but that's an opinion point. Um, it's the same in the Verilog, right? You can see that not in the Verilog over here. These Scala names end up becoming usually contiguous in the Verilog. So the maybe adder's a bad example. Let's look at R0 out, for example. Yeah, you see R0 out kind of stays together. So that's not going to have any impact on naming. Um, in the following lecture, we're going to talk about more ways to add structure to your design. Rather than having a flat list of wires like this, you might instead choose that additional structure. Say, okay, this is a port, and a port has, ports within it, right? And that kind of stuff. So we can talk about that in the next lecture. Yeah, that's a great question. So if I was to have the wrong bit width, how does this break? Let's find out. So if I have, let's say, only a 3-bit register specifier, I can't specify the entire 32. I only can specify 8. I think it's probably gonna be okay, and it's probably something we wish wasn't there. Let's see what happens. Yeah, probably something we wish wasn't there. You can see that because we only had 3 bits instead of 5, it put in 2 zeros in there. Yeah, and so that's probably not what you want. Yeah, that's an example. Maybe the tools can be smarter and warn us you're about to, blow your foot off. On the other end, let's say we have 64-bit outputs, but the registers themselves are, let's say, 32 or something. I assume it's also going to be zeros. Oh, I guess sorry, I got to rerun that and then rerun this. Yeah, it's also going to zero pen. So yeah, there are times when it's bit with mismatches, it's going to adapt accordingly. Now, in this particular example, I believe now I kind of want to pressure the width inference engine. Let's see what happens. So uh, if I leave that width off, that's probably okay. So it's going to infer that should be 32 bits based on that. Now I think where the fun one is, what if I put that width back and then remove the width here? That might be in there. Let's find out. It's not in there. That's wild. It did width inference into a memory. I'm impressed. I don't know if people are figuring out how to build CAD tools, but that's actually kind of wild. You declared a memory without specifying the bit width, and because it crawled around the design and said, "Oh yeah, this is feeding into a 64-bit thing. I should make the memory 64 bits wide." That's wild. Yeah, great point. So uh, it's the width inference as opposed to two things being specified. So if you specify both sides, it's going to respect that and then fill in zeros or whatever it needs to make it match up. If you don't specify a side, this width inference engine crawls around the design and tries to fill this thing in. So I think the question you are trying to ask is, wait a second, if I don't specify how big this is, will it know that should be 5 bits? That's the question you're asking. Let's find out. It didn't know. It's like, you know what? I can't figure it out. The width inference engine is like, I'm crawling around. I can't figure that one out. It couldn't figure it out. So there are limits. It is human, or not human, but limited. And so, yeah, there's a limit to it. Yes. Oh, if I'm worried about the compile time for my project, can I speed it up by having fewer things inferred? Um, Technically, yes, probably, but I think in the grand scheme of things, it's probably a very small percentage. Um, The Whitfin's inference engine actually is pretty clever. Sometimes in some cases will actually do like multiple passes, like trying to find a fixed point and converge. But there's so many things done in the compilation process. I don't think it's a large fraction of the time as on with inference. I'm not positive, but I think I'll be surprised if it's more than 5 or 10%. There's a lot of stuff that goes on under the hood, and that's what, and then my familiarity with those timing constraints are based on the Scala compiler compilation flow. With the newer circuit-based flow, I think where time is spent has been changed based on that MLIR-based code base. But yeah, cool. Um, so in the spirit of this class, make generators parameterized. Why not have n read ports, right? So in that case, we're going to make the port for the addresses a vector, so we have n of them, right? That's parameterized. Only still a single write port. Our output, of course, also is going to be a vector in order to handle these n different outputs. So yeah, we declare, our memory for each of the registers, and then for each of these read ports, we simply attach the output to, that thing being accessed. And so I'm going to point out one thing that's kind of an interesting consequence of this. Uh, Compare this code to, let's say, to prior, right? In some ways, up to opinion, this other one might be more clear, question mark, right? And this is an interesting software design pattern, right? And that is that sometimes you'd think that, okay, well, if I have everything specified, that is going to be simpler code. And if I have things parameterized, the parameterization is to make it more complicated. There are some scenarios where actually having things be more general and parameterized actually makes the code simpler, right? Rather than having this copy paste of all these different, ports and all these different signals for these ports, we have fewer ports explicitly labeled because we're using Vex to kind of handle that. So I could also make, two reads, and this is going to be the same thing we keep generating, but this code is, shorter. So something to consider. This is one of these things. I think if you go around the webpage, you can see this. I recommend highly the software engineering book by John Osterhout, and this is one of his principles he brings up. Is sometimes making something more general, even more general than you think you need, can actually make the code simpler. This is an example of that. Cool. Alrighty, let's see what else we can do. So wrapping up lecture 5, part 2. We've been talking about collections, right? We want to have groups of things. And now all of a sudden we're talking about, building real generators. Rather than just doing whatever we can do in structural Verilog, we're actually trying to build things that are doing some amount of smarts, right? You saw a second ago, we were changing the number of read ports in the registry file. And that's not just changing the input output ports on the modules, also changing the internal wiring to make all this happen. No problem. In the prior half of the lecture, you also saw us building things like a delay line and changing the registers, all generation time. So when it boils down to it, more often than not, you're going to use a Scala collection, probably a seek, right? In other words, you need end things in your hardware and you want to have them, a way to access them, seek, right? And it doesn't mean you can't access them by index. It's just a question of when you're using the indexing. If you're using indexing during generation time, Scala collections like a seek work. If you're absolutely sure you want to have the indexing in hardware done, in the hardware, yes, then use a vec or a mem. Um, it's going to actually put muxes in the hardware. Just because you want things in your hardware doesn't mean you can't and shouldn't use a seek. It's the fact you need the ability to dynamically index into them is why you need to use a vec. And I didn't talk about a whole lot today, but I said this mem is really just like, a reg of vec, right? Um, if you want an actual set of SRAMs or something like that, or BRAMs on FPGA, you're going to use the sync read mem construct. We'll come back to that later in this quarter. That's the way to actually get that behavior. Cool. Any last questions? Okay.